Okay, let's see about the components of hidden Markovic model. First, it's hidden states, which is actual conditions of the system, and then observations, what we can see or measure, and transition probabilities, as we've seen, likelihood of moving from one state to another. Emission probabilities is likelihood of an observation given a hidden state, and then initial probabilities is the chances of starting in each state. So the goal is, given the observation, we have to predict the most likely sequence of the hidden state. Now let's see about the implementation of hidden Markovic model. So we assume that the real weather, sunny or rainy, is hidden, but we can see clues like people carrying umbrellas or not. So first we set up 3 important things: how likely the weather changes transition matrix, and how likely we see umbrellas depending on the weather emission matrix, how likely weather is at start, which is the initial probability. And then, using forward algorithm, we calculate the probability of seeing the given sequence of clues, like seeing umbrellas on different days. After that, for each day, we guess whether it's more likely sunny or rainy based on the highest probability. In short, this code predicts hidden weather conditions from visible observation, also finds overall probability of what we observe. First, we are importing numpy for efficient array and matrix operation, and then we are defining a transition matrix where rows is current state, where sunny is 0 and rainy is 1, and columns are the next state. And then we define an emission matrix. Again, the states are 0 is sunny and 1 is rainy, and observations are 0 is no umbrella and 1 is umbrella. And then we define the initial probability, like it's 50% chance it's sunny at the beginning and 50% chance that it's rainy at the beginning. And then we have the observation sequence. This is a list of things that we have observed, like 1 means you observed an umbrella and 0 means there is no umbrella. And then we create a 2D array alpha to store the probabilities. Row is time steps, 1 for each observation, and column is states whether it's sunny or rainy. It is initially filled with 0. This is the initialization step. For time t is equal to 0, which is the first observation, initial probability times the probability of emitting the first observation from each state, and this emission matrix picks the 0 column corresponding to the observation 1. And then we have this forward algorithm loop for each time t from 1 to 5. For each state j, sunny or rainy, we calculate the emission probability for the first observation at time t in state j, multiplied by the sum of the previous steps alpha value, and multiplied by the transition probability from all states to current state j. For each time state t, which means for each time state for each state at time t, sum up the probability of getting there from all previous states and seeing the current observation. And then after filling the entire alpha table, sum the final rows values, which is the probabilities of ending in either states after the whole sequence. And then print the final probability we have calculated. So now we guess the most likely state at each time step independently. For each time t, if alpha t sunny is greater than alpha t rainy, we say it's sunny, else we say it was rainy. Thank you.